invited host colloquium talk. Today's speaker is, well, we thank Hülya Argüz to give us this talk, first of all, for accepting our proposal. Hülya Argüz is an assistant professor in the mathematics department at the University of Georgia. She got her undergrad in Middle East Technical University, and also she did masters there. After graduating from masters, she got another master degree from University of Hamburg and did her PhD at there as well. After finishing her PhD, she started as a postdoc in Imperial College in London, and then she got several other postdoc positions in University of Versailles, France, in IAS School, Princeton, and IST, Austria. She is working on algebraic geometry with the applications in mirror symmetry. So stage is yours, Hülya.
Thank you very much. Thank you very much for the invitation. It's a wonderful organization. Many thanks to all of the organizers. So today what I want to talk about is Quivers and curves and cluster varieties. Here's the plan of my talk. So the talk will be essentially about finding a relationship between two topics, one topic in algebra and another topic in geometry. On the algebra side, I will tell you about Quiver Donaldson-Thomas invariants or Quiver DT invariants, and I will tell you about a formula called the Attractor flow tree formula, which is a formula for calculating Quiver DT invariants using tropical geometry. And on the geometry side, I will tell you about enumerative geometry of cluster varieties. I will tell you how do we go from quivers to cluster varieties. And I will tell you about particular log Gromov Witten invariants of cluster varieties, which are invariants corresponding to counts of curves and cluster varieties. So the main goal of the talk will be to tell you how these topics, the one in algebra and the one in geometry, are related. So the goal is to arrive at a relationship between Quiver DT invariants and log Gromov Witten invariants of cluster varieties. So I will start by reviewing some background material to before describing what Quiver DT invariants are. I will tell you what quivers are. A quiver is a finite-oriented graph Q with a set of vertices, which we denote by Q0, with a set of arrows, which we denote by Q1. And we have a map, which we denote by S, which maps an arrow to its source, and a map T, which maps an arrow to its target. So here I plotted a quiver with 3 vertices labeled by 1, 2, 3 with a bunch of arrows. And Q0 denotes the set of vertices, and you see the arrows from Q1. So this is a quiver. When you have a quiver, you can talk about a representation of a quiver. This is an assignment of a vector space to every vertex V of the quiver, together with a linear transformation to every arrow or edge between these vertices. So if you have a quiver with just these 3 vertices, for example, then you can imagine you associate to every vertex a vector space. Say to the first vertex, I associate the vector space C, the complex number field, to the second vertex C squared, to the third vertex C. And then if I have in my quiver these 2 arrows, I also associate a linear, I also want the data of a linear transformation between C and C squared corresponding to this arrow, and between C squared and C for this arrow. So if you associate vector spaces to each vertex, to every vertex, and linear transformations this data is called a representation. And just some terminology, the dimension of a quiver representation is a vector which we denote by gamma. And this is just a vector recording the dimensions of the vector spaces you associate to the vertices. Like here we had C, it's of dimension 1, C square dimension 2, C is of dimension 1. So gamma in this example is 1 to 1. It's just a vector keeping track of the dimensions of the vector spaces you associate to vertices.
These dimensions are the complex dimensions, right?
Yes, it's the complex dimensions in this case, yes, of the dimensions of the vector space, yes. Right. Okay, so once we have this data of a quiver representation, you can talk about morphisms and isomorphisms between two different quiver representations, and they are defined in a natural way via using some compatibility and commutativity. So you can imagine, like here you have this quiver representation, you have 1, 2, 3. You can put another copy of 1, 2, 3 above it and ask between maps between 1 and 1, 2 and 2, and 3 and 3, and then you can ask commutativity between the squares you will obtain. And if you have automorphisms and some compatibility, you can define appropriate notions of morphisms and isomorphisms between two quiver representations. So we will look at all possible quiver representations up to isomorphisms of a given dimension and plus of a for a given stability parameter. And this stability, notion of stability, is defined as follows. It's due to kink. It says if you have V, a quiver representation of a given fixed dimension gamma, as you said, like here, it's the complex dimension of these complex vector spaces, in this example, for instance. And you define M to be the lattice, so Hom and Z, where N is the lattice Z to the number of vertices of the quiver. So in this example, you have 3 vertices, the lattice N will be Z to the power 3, Z3. And M is the dual lattice, and MR is the associated real vector space. So in the previous example, it would be R3. So if you pick an element theta in gamma perp in MR in this real vector space, such an element is called a stability parameter. Any such element is called a stability parameter. And you say your quiver representation is theta stable for this parameter if for any subrepresentation, any V prime, which is a quiver subrepresentation, you have the evaluation of theta with dimension of V prime is smaller than 0, and we call it semi-stable if it's smaller than or equal to 0. So theta is an element of M, and dimension is an element of N, so there's a natural pairing, and depending if it's smaller or equal, we define some sort of technical notion of stability. And then we want to form a space called a moduli space for a fixed theta and gamma. We look at the moduli space of all theta semi-stable quiver representations of dimension gamma. I will just give an example of what kind of invariance we obtain from such a moduli space in a minute. So in nice situations when this moduli space, which is the space of all possible quiver representations of a given dimension gamma and of which are also theta semi-stable for a fixed stability parameter, we define the invariance, the Quiver DT invariance, as the topological Euler characteristics of this moduli space, which is the alternating sum of the beta numbers of this moduli space. And the most significant property of Quiver DT invariance is that there is a piecewise constant dependence on the stability parameter. So based on the work of Koncevich-Soibelman, one can show there is a universal wall crossing formula. Namely, it says if you look at the real vector space MR associated to the dual lattice to N, then there's a wall and chamber structure. So it admits a structure like there is a decomposition of the space into chambers like I drew in green. And the Quiver DT invariants, as long as you stay in one chamber, remain constant. And if you jump to another chamber across the red wall, the Quiver DT invariants change, and the change is described by a concrete formula called a wall crossing formula due to Koncevich and Soibelman. Okay, so a question is there a nice sort of Quiver DT invariance which we can understand how to calculate easily, a primitive simple set? And such a simple set of Quiver DT invariants exists. They are called Attractor DT invariants, and they are defined as follows. So to define the simple DT invariance, I need to fix a basis for my lattice N first. So I pick a basis. My lattice N was the lattice D to the number of vertices of the Quiver Q. So I pick a basis which I denote by S1 as Q0. And so I define a skew-symmetric form on N, which is defined as follows. So the pairing of Si with Sj under the skew-symmetric form is defined as Aij minus Aj, where Aij is the number of arrows from I to J, and Aj is the number of arrows from J to I. So using the number of arrows, I can naturally define a pairing on my lattice. And now when I fix the dimension vector gamma, if I look at the chamber containing the elements, which is in MR defined by using the skew-symmetric form and the contraction of the skew-symmetric form by gamma, this gives an element in MR. And the chamber which contains this element in MR is called the attractor chamber. So in MR, you have this point, which is obtained by using the contraction of the skew-symmetric form with your dimension vector. And this point sometimes might end up on a wall, but you can perturb it slightly so it comes inside in the interior of a chamber. And then you call this chamber the attractor chamber. And by definition, if you take any parameter theta, any stability parameter, which is a small perturbation of this attractor point, then you define your attractor DT invariance, the DT invariance corresponding to this small perturbation, this stability parameter theta given by a small perturbation of theta. And this theory, the people who defined these attractor DT invariants showed that it doesn't matter which small perturbation you take, they're generally well-defined, these attractor DT invariants. Here are some examples of calculations, previous calculations done. There's work of Tom Bridgeland, who showed that if you have an acyclic quiver, which means you don't have any cycles in your quiver, because this quiver is not acyclic because there's this cycle, there's also this cycle. So in simple situations like this, when you don't have any cycles, then it is shown that the attractor DT invariance for any dimension vector gamma of this form, where you have all zeros and only one somewhere, they're 1, and for any other gamma, they're 0. And there are also several conjectures for other quivers due to some French people, Bouchard, Manchot, Pioline, and Moscow Pioline. They say if you look at a Del-Pezzo surface, a local Del-Pezzo surface, by definition, this is the canonical bundle of a Del-Pezzo surface. Then there's a procedure to construct a quiver with the additional data of potential function, such that the category of derived bounded category of the quiver representations is isomorphic to, is equivalent to the derived bounded category of coherent sheaves on your Del-Pezzo. And in this situation, the Quiver DT invariants are described concretely as the Euler characteristic of the surface S. So this conjecture was proven if you take as your Del-Pezzo just P2 for local P2. This conjecture was proven last year. So what we did also with Bousseau in our work last year is to prove a formula showing that if you want to understand the general Quiver DT invariants, which are more difficult to calculate, you can find a formula calculating them, relating them to a set of simple Attractor DT invariants. So if you have a quiver with potential, then if you take a dimension vector and a stability parameter, you can define your Quiver DT invariance as a summation of all possible decompositions of your dimension vector into simpler vectors. Say if your dimension vector is, for instance, 2, 2, you can decompose 2, 2 as 1, 1 plus 1, 1, or 1, 0 plus 0, 1 plus 1, 1, or you take all possible decompositions into vectors with integer components. And then there are some coefficients and there's some automorphism group arising, the order of group of permutation symmetries. And then there are some coefficients we describe concretely. And then here on the right-hand side, you just have the Attractor DT invariants of gamma i's, which appear in this decomposition. So this is a formula saying that you can calculate any Quiver DT invariant in terms of simpler as a sum over simpler Attractor DT invariants. And we describe these coefficients appearing concretely, combinatorially. These FR theta's are described in terms of tropical curves. So I will tell you just a little bit about tropical curves to say what kind of coefficients are these and how we describe them. So here's a little bit background on tropical geometry. Tropical curves are graphs. They're just some combinatorial objects. They're balanced graphs looking roughly like this, with the data of a weight function attached to each of the edges, such that you have some balancing condition around vertices, namely the weighted sum of the direction vectors around every vertex is imposed to add up to 0. So if you have weight 1 here, 1 here, 1 here, you just add up the direction vectors and you see they will add up to 0. And when you have tropical curves, you can talk about a tropical counting problem. So you want to usually count tropical curves of a given degree and type. The tropical degree is the set of all unbounded edges. So the tropical degree is the set of data of all unbounded edges. And the tropical type is the set of direction vectors of all edges together with bounded edges. So if you fix the degree, then you can show if you fix the unbounded edges and if you impose balancing condition, there are only finitely many possibilities for the direction vectors of the bounded edges. So you can see if you fix the degree, there are only finitely many types of tropical curves of a given degree. Like these are 2 examples where the unbounded edges are the same. but they're of different types because the directions of the bounded edges in the middle are different. But once you fix the unbounded edges and if you impose a balancing condition, there are only finitely many possibilities. And the goal is to fix a degree and appropriate constraints and count all tropical curves of a given degree and matching some constraints. And there is some work of Mikhakin and dimension 2 who first showed one can calculate such counts in a well-defined way, and Nishino-Zibet in higher dimensions who showed how to calculate tropically such counts of tropical curves. And in our story, we're gonna describe tropical curves using what we call flow trees. We are gonna describe families of tropical curves. If you remember, we had a real vector space MR and some gamma perp for our dimension vector gamma, some hyperplane in MR. And we have a stability parameter theta here. Now, using this theta, we are defining tropical curves by starting from theta and going in the direction of the vector determined by the attractor point. And this way, so if your gamma perp is this, whenever you have a decomposition of gamma perp into gamma 1 perp, gamma 2 perp, so you start at theta, you go in the direction of the attractor point. When you hit this wall, then you continue on gamma 1 perp, gamma 2 perp in the direction of the attractor points here. And this way, there's a combinatorial recipe to build tropical curves using the data of a stability parameter, gamma, a decomposition of gamma, and the attractor point. So these are sort of tropical curves we are building and counting to obtain the coefficients I mentioned in the attractor flow tree formula here. The coefficients are determined purely combinatorially by constructing and counting tropical curves out of this data of this decomposition. And in the remaining part, I will tell you how these coefficients are related to geometry and to counts of curves geometrically. Are there any questions until now, or should I continue? Do you hear me?
Yes, I think there is no so far.
Okay, perfect. So in the geometry part, okay, so we had this quiver Q, we had this lattice Z to the number of vertices in Q, and we had the dual vector space. And now we want to construct an algebraic variety, a space where we will count curves out of this data. So out of the data of the quiver, we first construct a toric fan containing all the rays are greater or equal 0 times vi, where vi is the vector defined by using the contraction of the skew-symmetric form at basis elements for this lattice. So the basis elements of this lattice define you a bunch of vectors, and you put all these vectors together in Rn to form a toric fan. And the data of a toric fan in toric geometry, this tells you how to construct the space and algebraic variety. And we look at the toric variety corresponding to this fan, and then inside this toric variety, we also use the data given by the quiver to describe hypersurfaces in the toric boundary. So there is this toric boundary device in this toric variety. And we define hypersurfaces given by the equation that I wrote here in this toric variety. And then we blow up these hypersurfaces in the toric boundary. And the blow up is defining us what we call a cluster variety. Namely, if you look at the total space of the blow up, which I denote by X, and D, if D is the strict transform of the toric anticanonical divisor, the complement is what we call a cluster variety. And in this cluster variety, we are going to count curves. So we're going to look at particular types of curves like this in X, which touch the divisor D at a single point. These are called A-bar curves. And they're defined, such counts are defined by Abramovich and Gross and Siebert. They have the theory of log Gromov Witten invariants. They tell how to appropriately count such curves by imposing appropriate constraints, and such counts define what we call log Gromov Witten invariants. And here's the main theorem of our paper, which will be available in a couple of weeks on arXiv. So this is current work. Just to recall, on the algebra side, we were looking at DT invariants of a Quiver representation. So these are defined using representation theory. These were the topological Euler characteristics of moduli spaces of Quiver representations. On the geometry side, out of the data of a Quiver, we construct an algebraic variety, a cluster variety, and we count curves in this cluster variety. And the main theorem says that some of such counts of curves, which give Gromov Witten invariance, is equal to the Quiver DT invariance. And I will just tell you a heuristic picture. So if you look at your cluster variety, X minus T, so the total space of the cluster variety is expected to admit a torus vibration of a MR. So you can imagine the total space formed by union of tori over the space, degenerating into over some points you have like pinched tori. And the space can also be viewed, the base of this vibration, also be viewed as the space MR, which we say is the stability space where we take the stability parameters of the Quiver. So DT invariance can be calculated using like wall crossing in this space, and Gromov Witten invariants are the counts of curves that I try to illustrate here. So they're expected to, in some appropriate tropical limit, project to walls here. So you can imagine heuristically, it was expected that the counts of curves are related to DT invariance of the Quiver. So we show this theorem using like analyzing Kontsevich-Zeubelmann's wall crossing formula and analyzing how counts of curves appear there and are related to wall crossing. I think this is all I wanted to tell you about today. Thank you very much for your attention.
Thank you.
Yeah.
Is there any question?
Ben bir şey sorabilir miyim? Bir yerde bir blow up yaptık ya sonlara doğru. O bildiğimiz genel blow up değil mi? Non-toric. Herhangi bir yerde.
Non-toric blow up, evet. Çünkü toric blow up yaparsak hep toric variety elde ederiz. Bu bildiğimiz non-toric blow up, evet. Bu çok iyi bir soru. Bu hypersurface'ları öyle construct ediyoruz ki bu hypersurface'lar bu toric boundary component'ın interior'ında kalıyor. Eğer onlar bu kesiştiği noktalarda kalsa, buraları blow up etsek toric blow up olur. O zaman hep toric variety elde ederiz. Çok ilginç sonuçlar vermez o. O yüzden genelde hep böyle hypersurface'ları bu toric boundary'nin içerisinde kalacak şekilde construct ediyoruz. Onları blow up ediyoruz. Bunlar non-toric blow up oluyor, evet. Elde ettiğimiz blow up sonucu elde ettiğimiz variety toric variety değil. bir başka deyişle. İyi soru.